Well, okay. Good morning, everybody. All right. Hopefully, you guys had a nice, restful weekend. And you guys are still safe. So let's take a look at what we've been doing. Let's go to what I call let's go to the browser, right? Let's see what's going on with the browser. Let's go to the website. So here we are at the website, and I'm going to go to Math 262. And we're going to go down to online transition. And what you guys should see down here is we got surface area. These are the notes. I got the YouTube lecture surface area here. And then notice clicking on this, we have some examples here. So what I did for you guys this weekend is I did some additional examples, but this time it's going to be on video, just like I asked you guys, or I promised you guys, right? So I made this promise to you that we were going to have these videos, and I did. There's another about 5 or 6 examples. Looks like 12 of you guys have maybe viewed it already, which is good, and it's about an hour additional work here for you guys. So it's not in PDF format like the other examples. It is in a video format, and it looks like we already have one person who loved it. I'll make that now too. Anyway. Okay, so there are additional examples. I believe I did that as well for the arc length. So go back here and you go, oh, okay. Additional examples for arc length as well. So we got 25 views. Some of you guys maybe have looked at that. And 6 likes, now 7, right? So you do have additional examples for both arc length and surface area to absorb. Hopefully you guys worked on some of that this weekend, right? Because we're going to need to use some of this information, and they're very good problems to do. There's just a little bit of algebra that people have to remember how to work with, and that's the trick with some of these, doing some algebra. So anyway, that's the information I have for you guys regarding the videos here that I said I'd upload for you guys. So make sure that you look at that. And then you have what we're going to work on today, which is called parametric equations. And I also have the calculus of parametric equations. So we're going to look at parametric equations and even, polar equations eventually. But both of these equations are systems that we use to describe curves and graphs, because everything that you guys studied, like circles, parabolas, ellipses, lines, in terms of graphing, is not the only curves that exist, in mathematics or science. There's a lot more out there. There's a lot more out there that you don't know than those that you do. So we're starting to open the door a little bit for you by introducing to you some additional curves. And in order to do that, you have to actually think a little bit outside of the box to do this. And that's where your parametric and your polar curves come from. Okay, you are thinking a little bit outside the box, and we are, looking at what that brings us. It's really just additional curves. So I want to say to you guys, remember, make sure you do the arc length, surface area, because it's going to be applicable for other things in the future. But that's kind of where we're at. So I also want to remind people, if we go to our schedule here, and so we are in April 27th, which means comes next week on May 4th, you have your third test. So also make sure you understand some fundamentals, because this is something you're going to need to know how to do, right? Understand how to use your smartphones to take a picture of your exams so that you could submit your exams, right? So you have to be functional with that. So make sure you guys are good to go with those kind of things, because, this is going to creep up on us. So I'm just kind of regrouping here with what we have done and where we're headed and what's on the horizon. So we're going to get some work done. So glad you guys are back. And this morning I plan to, again, if we go to the online transition, take a look at, some parametric equations here for you guys today. Now, this is what we have online here. I do have it in the iPad as well, but let's kind of maybe take a look at this for now to see what this really is about, okay? And these lecture notes are there for you as well. So what we're going to look at is the following, okay? Essentially, the rectangular coordinate system is a system you guys already know and love. And maybe let's see what happens. Yeah. If we go to the iPad version, let's see. And if it's not, yeah, okay. So, not sure. That's a little weird. Doing that same little weird thing like it did last week. Okay, I'm going to go to the browser. Apologize for that. We're going to have to go to the browser. I'm not sure exactly what that stuff is. It just doesn't seem to like, yeah. Let's try this quickly. Yeah, see, that's a little bit weird to me. I don't like the quality. So I'm going to have to read through this on the browser. All right. I wonder if I PDF that file, if that'll be better. That might be it. Maybe if we do a nice PDF. How's that? we could PDF it. 262. And I'm going to go to the iPad again, but this time I'll be here. And PDF file. Well, that seems to be a little bit better, but not much. All right. So today, what I wanted to show people is, let's go through some of these definitions here, right? Essentially, we're going to describe curves here parametrically, where x here is going to be some function of some time t, y is another function of t, and then t is going to be into some arbitrary interval, and that's how we write this. In other words, a is less than or equal to x, or I should say, let's go back here. Does this look a bit blurry to you guys on your end? I'm going to ask you guys about this. Does it look a bit blurry? Because I'm about to transition here. If it looks it looks blurry on my end, which I'm not happy about. So here's what I'm going to do. It looks a bit blurry. So here's what I'm going to do here. If I go over here, yeah, it's a little blurry. Okay, I'm going to go out to. I'm going to have you guys look at the browser here in the notes as I do a few things here. I'm going to try to see if I could fix this issue. And in order to do that, okay, I need a code. So I'm going to try to fix this. Okay. Huh? Okay. So that's weird. And okay, so all right. It looks like this is tons better. Okay, so let's make this source. All right. So thank you guys for being so patient. This is such a pain. Kind of not sure exactly what's happening there with this. This is a lot better. So I do want this to be clear because I spent a lot of time and energy with this work last week and this week. And I want to make sure that you guys can see this very, very well. So here you guys go. Here's where we're at. We're looking at curves here. This is normal, where you have something called C. And C here is going to represent essentially a curve. And if you notice, the rectangular coordinate system here is what you guys are looking at. This is the X variable. This is the Y variable for every point that you guys plot. And that's the point we're looking at right here. So there's the X coordinate, the Y coordinate. You guys know about that. What is new and what is happening now is simply that we are introducing a parameter, another variable. And that's what that means. A parameter is just another variable. T, sometimes with physical applications, T represents time. But here, we're just going to stick with T. And when I have here, T here is in some interval, well, that's what that means. T is actually an element of any interval. Now, intervals can look a lot of ways. It can look like something like this from A to B. T could be greater than or equal to 0. T could be greater than 0. And T could be really between, well, here's what we say. T could be any real number. So there's various intervals for that parameter T, also thought of as a dummy variable. But we're going to, introduce this because this is going to create for us additional types of curves. Okay, so that's kind of the idea here behind this. And nevertheless, that's what's happening with this. So notice how I define those now, right? Your X coordinate is going to be some function of T, and the Y coordinate is some function of T as well. And this should be actually F, by the way, and this should be G. So this is something I have to go back and fix. But, writing all your material down here is such a challenge. Nevertheless, let's look at some definitions here, okay? Because it's going to help us consider these curves that we're going to be working with, right? We have various types of intervals. We talked about that. I have a definition of what's called an initial point. So if your T variable here is going to be between two values, right? Between A and B. Well, the smaller value is a. So we say f of a and g of a, because remember how we define the x-coordinate and the y-coordinate, right? For that smaller value, this is called an initial point. It's an initial point on your curve. If you look at the b value, the upper bound, similarly, f of b and g of b for that particular b value is called the terminal point on the curve. So when you have these kind of intervals, we can have an initial point and a terminal point that we're concerned with on the curve, but we also have something known as the orientation, and we're going to look at this today. So we're going to look at these kind of ideas. We're going to look at, the x-coordinate, the y-coordinate, represented as some functions of time t, and this thing called orientation. And the orientation is the direction at which the point travels as t increases. Now, t is always going to increase for us, ladies and gentlemen, meaning t gets smaller to larger. This is how we wrote down the interval, right? A is less than or equal to t, which is less than or equal to b. So we're going to look at these things called like an orientation of a curve, initial points, terminal points. We're going to investigate what these curves look like, and that's what I wanted to spend the day here with this morning. Anyway, okay, so let's kind of look at some examples here, right? So here's what I wanted to do. This is why I want you guys to be able to see these things. Here's some interesting parametric curves. We're going to look at a few of these. And some of these you may recognize, and some of these curves you may not recognize, right? So there's some very interesting things that we can see now. Now, I don't know about you. I don't recognize this curve. It doesn't really, it's not something we studied in trig. It's not something we studied in intermediate algebra or pre-calculus or even calculus 1. This is a parametric curve. And it's defined this way. The x-coordinate is cosine t, and the y-coordinate is really sine 2t. And I want you guys to note something, that if you note, t here is silent. They don't give an interval here for t. And so you don't really have an initial point. You don't have a terminal point, right? Because it's silent. There's no t. And sometimes they do that. They won't give you an interval for t. What that implies is that t is any real number. That means t can be over that kind of interval, right? Negative infinity to positive infinity. That's what t is going to be. So that's what's going on here with this curve. And so that means we can't look at some of these two definitions, initial point, terminal point, but we can consider orientation. Okay? Because if we start to plot points, and that's what they would want you to do ideally, and I'm not going to do that, okay? Your book has an example you guys can look at about how to start to plot these points. Here's what the book will say. It'll say, okay, you have a formula for x, you have a formula for y, you have a formula for t. This is what your book does. And then they'll tell you plot points like you did your whole life in every math course, right? You had to plot all these points all the time. If anybody remembers that. And you could start doing that too here. But I'm not going to waste the day and time by plotting a million points for different curves. But if we're going to talk about the orientation, I'm going to do something here. We're going to start by letting t be 0. So that's a starting point. This is time or t. I mean, we can't even think of it as time because time's never negative. It's always positive. But if I plug in 0 here for t, we can see that x becomes cosine of 0. And cosine of 0 is 1. And then y becomes sine of 2 times 0 is 0. Sine of 0 is actually 0. So here's what this means. When t is 0, the first point, or I should say a point on the curve, happens right over here. This happens when t is 0. So this is the starting time. In some sense. Not exactly, because this is over all real numbers. But I can start to look at my orientation because I want to see what happens to the points as t increases. So I'm going to increase my t. Now I'm going to do it in such a way that, let's say here, let's say t is going to be pi over 2 now. I wonder what's going to happen to my t. So if I plug in now over here, t being pi over 2, we get cosine 90 degrees, cosine pi over 2. Cosine 90 degrees is 0. So the x-coordinate is 0. And let's say, what's the y-coordinate? Well, sine of 2 times pi over 2 is sine pi. I think that's also 0. And sure enough, somehow, we're now at the origin, and this happens here when t is pi over 2. Now, ladies and gentlemen, this is an issue for us. Let me tell you why. Because either we did the following. Either as time increases, the points were defined either in that direction, called an orientation, or they went in the other direction. So this is what plotting points does for you. And so we have to figure this orientation out. Okay? So what I'm going to say now then is you say, well, what do you do to figure this orientation out? Which direction did the points travel, if you want to think of it that way, as t increases? Well, let's erase this. Here's what I'm going to suggest we do. Use another value for t. And maybe we're going to say, well, what happens when t is pi over 4? All right, you guys okay with that? We're going to plug in pi over 4. So let's see what this does for us, because we may need to do some arithmetic here, right? Remember what this was. X is cosine t. Y is sine 2t. We're going to look at when t is pi over 4. So when I plug in pi over 4 here for both x-coordinate and y-coordinate, we're going to get some values here. So that means x will be cosine pi over 4, and y is going to be sine of 2 times pi over 4, and that means a couple of things here, right? So x is cosine pi over 4, which is 45 degrees, and y is going to be sine pi over 2. Okay, I know this one. This is easy. Sine of 90 degrees, that's 1. Cosine of 45 degrees, though, you guys have to remember, what is cosine of pi over 4? Anybody know? Isn't that 1 over the square root of 2, which is the square root of 2 over 2? And that's approximately, if anybody knows, right? What is this approximate value? Double check, because I'm not awake yet. Anybody remember what this value, numerical value is about? Right? It's about 0.7. So the x-coordinate's about 0.7, and sine looks like it's about 1. So if I go back, the x-coordinate, 0.7, and sine is about 1. So 0.7 is not quite 1. And so here's what this looks like. When I go, here's where 1 would be. When I go to 0.7, I have to also go up 1 unit. And so 1 unit looks like, these look like it's going to be, how many units is this? This is 1, this is 1/2. Oh, okay, I'm actually wrong. Let's be to scale here. Right, 0.7 is actually close to 1. So 0.7, and I guess somewhere, is that 1? Let's see if we can take a closer look. I guess it's more closer here. Okay, here's my point. This happens when t now is pi over 4. So it looks like the curve here, or the orientation now, is actually going this way. Now I don't have to check any more points, but as you guys can see, as t increases, it's going to trace out this shape forever. So I just found the orientation by plotting values of t, starting with arbitrary values of t, and looking at the points that's generated by doing that. And this is kind of the start of how we want to work. So I'm going to say this is when t is 0, right here. We already noted that. Over here, t is pi over 2. We noted that one too. And so we're getting an idea of how this is oriented. But this is how you always start. Okay? So there you guys go. Here's your first example. And this is a curve, you know, it looks like infinity, right? But this is one of the curves that you may not have been familiar with. We're starting our world of parametric equations here. Now go to the next curve here. Here's another interesting curve. And ideally, when I work with this stuff, I mean, maybe it's, I'm going to try to see maybe how PDF files work. Maybe they work a little better. But here's another parametric curve that you guys are looking at. Okay? However, if you see, t now goes from 0 to 2 pi. So we know we have an initial point, and that happens when t is 0 here. So the initial point is going to be 2 times cosine of 0, comma, 0 minus cosine 0. Here's my initial point. So I'm going to look at the curve here. I'm going to find the initial point, I'm going to find the terminal point, and I'm going to find the orientation. So I'm using the definition of initial point. Plug in that value. Cosine of 0, though, is 1. So this means we have 2, and 0 minus, I guess like it's negative 1. So 2 negative 1 is the initial point for this curve. So you go, okay, where's 2 negative 1? Well, go to the right, 2, 1, 2, go down, negative 1. This happens when t is 0. So I'm going to make a guess here. Here's kind of something I'm going to guess. We're going to use some common sense here. For this curve, it probably is going to go in this direction as t increases. So I'm going to plot these points as t increase. Here's the initial point. We get the terminal point now by replacing t with 2 pi. So wherever there's a 0 now, I'm going to replace that with 2 pi. Wherever there's a t, really. So if we want to get the terminal point, we can say terminal point will be 2 cosine pi, comma, pi minus cosine pi. And you have to remember what's cosine pi, right? Cosine pi, I believe, is negative 1. So we get 2 times negative 1. See if it comes out. It doesn't like to write on a corner. 2 times negative 1 is negative 2. And then you're going to say pi here, ladies and gentlemen, minus, I thought we just said cosine pi was negative 1. It is. So that's plus, minus the minus makes that a nice plus now. So that's plus 1. So let's double check to see if our arithmetic is okay this morning. So looking at this curve, defined parametrically, we get pi plus 1. Now remember what pi is. So if I said, okay, 2 pi is about 6, what is this going to give you? Right? The point negative 2. Pi is about 3, so that's 4. So we go up 1, 2, 3, 4. It's a little bit more, ladies and gentlemen. So here's my point. -2 pi plus 1 is approximately 4. It's a little bit more. This happens when t is actually 2 pi, ladies and gentlemen. So let's write this down. This special point is my initial point. Here's the terminal point. And like I said, the orientation, the direction of travel as t increases for any point on this curve starts right here and ends here for the interval that they gave us. That interval is going to be between 0 and 2 pi. So here's an example of a parametric curve, something we don't recognize, something we've never seen before. And this is how we use our definitions, right? Initial point, terminal point, and this direction of travel is the orientation. Now, if you increase your t, it's going to keep going. And actually, sometimes students will say, okay, Mr. Judge, I know we looked at the interval from 0 to 2 pi, and this really is the curve from 0 to 2 pi. Okay? However, what might have happened is that the curve, you went all the way to this point and then came back. In other words, for some t value, you may have been way up here and you bounced back and you're coming back in that direction. So we're going to see some things that look just like that. So I just want to give you a little remark, only that there might be some more information about this curve. And we're just getting started here by looking at the initial point, the terminal point, and the orientation. All right, so here's another curve. And this parametric curve you may not recognize, and we want to start to see how this behaves. And notice what they gave us, right? We got -2 and +2. This is our interval. So for the x coordinate, or the initial point, let's start to put it up here, right? Your initial point, plug in 2, or I guess -2, right? Wherever there's a t. And then your initial point is going to be e to the minus -2, right? -2, comma, e to the -2 plus a -2, which is going to be -2 again. So we can write that down. So we get e squared -2, comma, e to the -2 minus 2. So here's our initial point on this curve. Terminal point, and maybe we should just plot this. Where would that be? Remember, e is about 3, so this is about 9 minus 2, so we look at 7. It's kind of off this chart. And then here's what I'm saying to you guys. Here's going to be something where you have 9 minus 2. Yeah, let's double check. T is -2. So it's about 2.78. It's a little bit more. So 9 minus 2, it's about 5. It's a little bit less, sorry. And this will be really 1/9 minus 2. So it's 1/9 minus 18/9 maybe. This is a very bad approximation, but it's a -17/9. It's going to be less than that. So it's about 4. It's about over here, so you guys know. Okay? So here's our initial point, and that happens when t here is -2. So there's the initial point. Terminal point now. Plug in the other endpoint. 2, 2, 2, 2. We get e to the -2 plus 2, e squared plus 2. And this is going to be, again, about 1/9 plus 2. And this is 9 plus 2. Very bad approximation. 11. And this is going to be 18/9. So it's 19/9, comma, 11 maybe. Very bad approximations. Let's double check that e squared. Now 2.7846. Yeah, I'm actually going to say if we really did a better value, because e is about going to be 2.718, so it's extremely bad. You're actually looking at something I believe to be over here. And this is going to happen where t is 2. So notice that the only way you could go from this starting point to this terminal point here is for your orientation to look something like this, so you guys know. These are very bad approximations over here, okay? Because e being about 3 and squaring that 9, you get 11. Now it's about 2.718. You could do a little bit. You could do better than that. But my point I'm making is here's another curve defined parametrically. You've never seen it. You can find the initial point. You can find the terminal point and this orientation. And that's going to be something we need to know. Okay. Well, let's go through some other curves here and notice how interesting this family of curves is. I'm not going to do the work here for this, but that's something you've never seen before. Okay? It's a very interesting curve. We can actually perform calculus with this curve. Not today, but, you know, I want to introduce you to parametric curves. Okay? All righty. Anyway, let's see what other curves we have. Here we go. Oh, sine 2t, y equals sine 3t over the interval -6 to 6. Look at this curve here. Okay, here's a fantastic curve that we've never seen before. We could even do calculus. We can do a lot of things with this curve. We will. But today I want to introduce you to parametric curves. Talk about initial points, terminal points, orientation. Get you guys used to this because, you know, you study this in trigonometry, or at least you should. And some people, you know, may do that. Some people may not. But, you know, the world of parametrics is, as you can see, fascinating. Here's another very famous curve. T is arbitrary. It's silent. You say, what do you mean? There's no mention about an interval. So that means t is any real number. All right, just to point that out and take a look at this now. This is a very, very famous curve. This curve has a name. It's called a cycloid. There's a family of curves that behave in this way, that look this way. It's a cycloid. Okay, and it's in your book. Let's dig out those family of curves called cycloids. All right, we got a cycloid. And here's your definition of cycloids. X is a plus cosine of t Oops, sorry. Not at all. Let's get the definition. X is r t minus sine t. And y is r 1 minus cosine t. Anyway. And r is, of course, related to the radius of a circle. T is actually an angle, and your book will probably use the version that you have theta here anyway, because they're going to have that as theta or t. Doesn't matter, but you got a cycloid. Okay? And that's something you may not have seen before in your life. We could use calculus for this too. All right. Now, we're going to get into some curves here that might be familiar. This is familiar. This is a line, ladies and gentlemen. You say, okay, I know that's a line. Well, when you plug in your t value, let's find the initial point, right? This happens, t is -2, so my initial point, I'm plug in a -2 for t. So for my initial point, you guys can see we get 1 minus 2, right? And then we get 5, really plus 4. So for the initial point, it's -1, 9. So -1, 9, here's where -1 would be. 9 is up here. Here's my initial point. It happens when t is, I believe, -2, right? Okay. Now what happens when t is 3? So maybe we should just change the color. Plug in a 3 for t now. So for the terminal point, we're going to get 1 plus 3. And we get 5 minus 2 times 3, which is 6. So the terminal point is going to be 4, -1. Okay. And sure enough, let's double check. 1, 2, 3, 4, -1. There you go. Sure enough. Terminal point happens when t equals 3. So your orientation looks like it's going in this direction. Here's the orientation of this curve. However, this is a line segment, ladies and gentlemen. It's not a line, it's a line segment. So for the line segment, I want you guys to know, here's what's going to start to happen. They're going to start to ask us certain questions, and maybe we can start to write it down. What curve is this? Since you recognize it, you say, I know what it is. It's a line segment. But can you define that? Can you define that curve? Can you give me the equation of the line that represents this? And the answer is going to be, ladies and gentlemen, yes. So I want to kind of transition to show you that for some of these curves, we could define what they are. And here's the key. Use algebra. Solve for t. In other words, go back over here and over here. There's a couple of ways we can do this. I can say to you, I can solve this equation for t. That means t will be simply x minus 1. So double check to see if I'm right about that, right? All I did was subtract 1 from both sides. So if t is x minus 1 for this first equation here, right? Start here. This is what I'm saying. Now you're going to go back and substitute for t in this equation. When you do that, you get y equals 5 minus 2 times x minus 1. 5 minus 2x plus 2, or you get y equals 7 minus 2x. So this is a linear equation, ladies and gentlemen. It's a line, but this is a line segment. It's a line segment because they're saying this is only good from -2 to +3 in terms of that t value. So that will define this particular line segment that you guys see here. So some of the curves are going to be familiar to us. And take a look at this curve here. You might say, well, that's half a parabola. It is. What is that? Well, we already know it's half a parabola here, right? Just by looking at the picture. But what we can do now is the same sort of thing. I can go up here. And I guess we changed the color, which is why I'm solve this for t. So if x is the square root of t, square both sides, and we get t is x squared. And you guys know, what do you do with that t? You can substitute it. So when you substitute, you end up with y equals 1, not minus t, but minus x squared. This is the curve they're talking about. However, you have to be careful here. T, though, if I said to you, what is the value of t? What's t good for? It's silent. If you said, oh, t is any real number, I'm going to say to you, no, that's not true. Because we have the square root of t here. And that means t has to be simply greater than or equal to 2. So this is how we start looking at this curve here. So t is greater than or equal to 0 now. Okay. The initial point, though, if I say, what's the initial point? We'll start when t is 0, right? That means for my initial point, x is 0 and y is 1. Here's my initial point. There's no terminal point because there's no upper bound on the variable t. So when we start at 0, 1, this here is my initial point. This happens when t equals 0, and the orientation looks like this. Sorry about that. Let's turn that phone. I thought I turned that phone off here. Okay, let's turn the phone off. There you go. So here's my orientation because there's nowhere else for this curve to go. The t is 0. Here's my initial point. All right, you guys okay with that? Anyway, here's one of my favorite pictures. If you look at this, this is called a semicircle. And look at the equation we have here for this. X is sine t, y is cosine t. T is defined between 0 and 2 pi for this particular picture. So at this point, let me remark, even though I know it's a semicircle, I can verify that. I could use algebra. Because since x is sine t, right, this means x squared is cosine squared t. I can square both sides. Same thing for the y-coordinate. Y squared will be sine squared t. Okay? So I can determine this equation by simply now adding x squared plus y squared. And I'll get cosine squared t plus sine squared t. Or x squared plus y squared will be 1 because on this side, I have a nice identity. This is 1. So you're looking at the equation of what we call the unit circle. Centered at the origin, radius 1, right? Because it's of the form x squared plus y squared is r squared. And r, the radius of your circle, has to be positive. So this distance is 1, and that's negative 1. So from 0, though, to pi, we can get the initial point to be sine 0, cosine 0, right? Plug in 0 for that t. We get 0, 1. So for the semicircle, you start here, 0, 1. This happens when t is 0. That's my initial point. Now, the only way we can go and trace out this semicircle is, if you guys notice, the orientation has to go this way. So that looks like it's going to be, here's what we say for a circle, counterclockwise orientation. So it's counterclockwise. The terminal point happens when t is pi. So I could go back here and say, okay, let's plug in pi now. So for the terminal point, we end up with sine pi cosine pi, where the sine is 0 of pi and cosine pi is -1. So that location, 0, -1, is right over here. That happens when t here is pi. So let's kind of go back a bit and say, here's my initial point, here's my terminal point. We have counterclockwise orientation. So this is the parametric form for what's called a semicircle. Now, I want to note something because sometimes people say, how would you get the full circle? Well, if t now was 0 to 2 pi, you'll get the full circle. So some of these curves, yes, we do recognize. Here's the full circle, 0 to 2 pi. And so you already know from the prior example that my initial point happens to be here, t is 0. We have counterclockwise orientation. And you might say, since this goes from 0 to 2 pi, the terminal point is also sine 2 pi, cosine 2 pi. Here's my point, 0, 1. The terminal point is the same as the initial point. So you start and end at the same place. And again, this is counterclockwise orientation. So your curves can really intertwine for various values of t, meaning this is not well defined. Okay? Every point can be defined theoretically with multiple t values, depending on the parametric curve. For a circle, they can define this. They can say to you, here's a note, if you had an interval now, 0 to 4 pi. This is going to give you a curve that's transversed twice. Meaning you went around that unit circle 2 times. And if you don't believe me, plot some points and verify, right? So what can happen is they can change that t interval on you. It'll change your initial point. It'll change your terminal point. You'll have some orientation, but it can cross multiple times depending on the curve. Now you say, what's this curve? X is sine squared, cosine squared. You square both of these. Well, here's what this looks like. This is a line segment. And that's a line segment. Yeah, that's a line segment. Okay, you can actually show that that's a line segment. Maybe we'll have you guys show some of that stuff and think about why that's a line segment. My initial point on this curve happens, they don't even give me, there is no such thing as initial point because they don't even give me an interval. So remember, t now is any real number. Now you might say, well, how do I show the equation of the line here? In other words, for the ones that I do know that look familiar, maybe I'll just show you guys here. Take a look. Tell me if you guys agree with this. Isn't x over y sine squared? Well, maybe we should do, let's not do it that way. Now you guys can do this. This is kind of simple. Say simple. Isn't x plus y sine squared t plus cosine squared t? Or we can say x plus y equals 1, which means y equals 1 minus x. This is not the iPad well, it is the iPad, but it's not notability. So that means my lines here, right? So there's a curve that you may recognize. But it's a line segment. So I want you guys to think about, why is this a line segment? T could be any real number. What's happening is that these points are bouncing back and forth forever on this curve. You can figure out the orientation. You say, how do I get the orientation? Well, let t be 0, let t be pi over 4, find an x value and a y value for each. You say when t is 0, you know, what do we get when t is 0? We get sine 0, so that's 0, 1. So here's where you'll be when t is 0, but t could be any real number. It could even be a negative value. So just want to let you guys know that on this line, the point is actually oscillating forever. Okay? Oscillating forever for various t values on this thing. It's going back and forth forever. So the orientation could go this way for various t, and then it bounces back for different t. It'll come back. It just oscillates forever because t is any real number. And so you have another curve, and you say, I recognize this curve. That's a hyperbola. You go, so really, this is the equation of a hyperbola? It is. And I can ask you guys to think about how you prove that, right? How do you prove this is an equation of a hyperbola? Well, you might be able to guess. You might say, should I square? Right? Should I square both sides? Isn't that a nice hint? And so, at this point, what identity can I use here? So if I said this to you, what could we do here? How about if I do this? Anybody know a nice trig identity? So I'll write that in words. If you know sine squared t plus cosine squared t is 1, divide both sides by cosine squared t, which really means divide both sides, every term, by cosine squared t, right? You guys remember this identity? You get tangent squared t plus 1 equals secant squared t. Which means tangent squared t is secant squared t minus 1, right? Or you could use the other way. So there's a couple of things that we can say here. So I want to ask you guys, how would you do that, right? Here's what I think I would do. And then now that means, if I put this all together, let's change the color. X squared equals tangent squared plus 1. And then tangent squared, we know, is right here, is y squared. So x squared is y squared plus 1, or x squared minus y squared is 1. So sure enough, we get the equation of a hyperbola. However, if you notice, there's no t value here. So t could be any real number. So there's no such thing as an initial point or a terminal point, but there will be some orientation with this hyperbola. How points travel. Now you can find that by starting, you can say, how do we find the details of that? Well, you can say, okay, start with t is 0, then go to t is pi over 4, right? And keep going. T is pi, and then you have negative values. T is negative pi over 4. Let's say pi over 2, negative pi over 2, and so on. So you're going to see how this is traced here for various values of t, and this is how we look at parametric curves. think we did that one already. Ah, what is this? This is the equation of an ellipse. You say, well, how do I do that? Well, if I divide both sides by 4, I get x over 4 is cosine t. Divide both sides by 3, y over 3 is sine t. And then square both sides. You say, what do you mean? Well, x squared over 16. Well, let me give you the details. You get x squared over 16 will be cosine squared t, and you'll get y squared over 9 is sine squared t. So that when you add these, x squared over 16 plus y squared over 9, you get cosine squared plus sine squared, and you know what identity to use here, and this is 1. So sure enough, you notice that we have x squared over 16 plus y squared over 9 is 1. And that means that this point here should be 4 minus 4, 3, negative 3, because this is the equation of an ellipse. And we don't have a value for t, so t is arbitrary. T is any real number. So you don't really have, again, an initial point or a terminal point. So you can start to get an idea of the orientation if you said, well, what happens when t is 0? Well, plug in 0. You get 4. Looks like it's going to be 4 comma 0 here, right? 4 times cosine 0, 4 times 1. 3 times sine 0, 3 times 0. So you're at this location here when t is 0. Don't say pi, try pi over 2 now. If we try to get the orientation, I'm going to plug in pi over 2 here now for t. 4 times cosine, that's 4 times 0, which is 0. 4 times sine, or 3 times sine of 90 degrees, well, that's 3 times 1, which is 3. So you're now at 0, 3, which means you're here. So this happens when t now is pi over 2, plugging these things in, and this is your orientation. So your curve here has this type of orientation. That looks like it's a counterclockwise orientation here. So you're going around that ellipse forever. And so this is describing orientation. So what I wanted to do here this morning to you guys is introduce you to the definition of, these parametric equations and show you how various equations look. Take a look at this one here. Notice what we did. T is negative pi over 2. T is pi. It's the same curve. But it's still the equation of ellipse. It just doesn't go all the way through. And you could do that. So if you said, how do I find the initial point again? Use your definition of initial point. For cosine negative pi over 2, 3 sine negative pi over 2. Terminal point. 4 cosine pi, 3 sine pi. So you can find these terminal points here, initial point, and the orientation. Cosine, what is that, 90 degrees? Anybody know what cosine of a negative 90 degrees is? I know cosine 90 degrees is 0. I think this is 0 here. So this will be 0. And then sine of negative 90 degrees, that should be 0, negative 3. t here is negative pi over 2. And I'm going to say to you, this is going to be here, t would be now, this is going to be your terminal point, by the way. That happens when t is pi. You could double check and verify this. We still have the counterclockwise orientation then. Right? So double check. Cosine pi. You go, what is cosine pi? Isn't that negative 1? So this would be what? Negative 4. And then sine of pi, that's 0. So negative 4 is 0. Sure enough. Yes. So you still have the equation of an ellipse with various t values, and you get the initial point, terminal point. We already proved that this is an ellipse, but you have a lot of curves to consider, a lot of curves to look at, and I want you guys to look at this today. You can even find this equation. You know this equation here very simply, right? We can show you how to do that. Not a big deal. You can find what that equals. And I gave you a lot of curves to look at. Here's a circle that's not centered at the origin. How do you find that equation? You can toy with that today. And then you have this this parabola. So you guys can find those equations like I showed you earlier today with a lot of these. Stuff that looks familiar. Here's another parabola on its side. You can solve for, write these, y as a function of x. And that's what I'm going to say to you guys. For homework today, I'm just going to have you guys do a couple of things here, right? For this worksheet, for homework, I want you guys to write the ones you recognize is y as a function of x, like we've been doing. You get rid of the parameter t. And then for some book work, you could do 11.1 on some book work, which is the same kind of stuff, like 5 to 30. No, it's like 5 to 21 odd. You could just do the odds there, but it's very similar to what we just did. Okay, they're going to want you to consider sketching some of those curves the way we did and look at this and look at the orientation and look at plotting initial point, terminal point. So I want to remark, this is kind of what I wanted to let you guys do today. And again, those of you guys that might have came in late, let's go to the browser and remind you of a couple of things. In the browser, what I want you guys to do here, let me move this out of the way, is notice that I put examples for arc length and surface area. And for both of these, they're video examples. Okay. So they're about an hour each of additional examples just for you guys for both of these topics, like I promised you guys here. Okay, so you can refer to some of those examples, and that's some work you guys need to be prepared to do as well. So I did put it up, like I said, and again, if you have any questions, come during office hours. And I really like the way the quality came out today, this morning, with this, because it was not, it was very clear on my end. Okay, what I'm talking about, the iPad portion is very clear. I can check that online here for myself, and we're going to try to continue with this so that it's clear for us from here on in. But anyway, double check, ladies and gentlemen, some of this work, and check the surface area, check the arc length formulas, because tomorrow we're going to start with calculus with parametric equations. We're going to find, arc length and surface area for parametric equations. We're going to find the length of a curve, right? We're going to differentiate. We're going to find derivatives. We're going to find second derivatives. We're going to start to do some calculus. But today you need to be introduced to the parametric curves. You need to look at points on the curve, initial point, terminal point, and consider orientation so that when we work on the calculus, it'll actually make a lot more sense to you. All right, so we're laying the foundation for you guys, okay? And I'm glad you guys are back. Have a good day. Again, see me during office hours if there's an issue. And, if you can't get in, email me and I could let you in the door. All right? So take care. Have a wonderful day. It was good seeing or hearing from you guys today. Okay?